Hello, everyone. My name is Pawel Gora. I'm a researcher from the University of Warsaw from Poland, Faculty of Mathematics, Informatics, and Mechanics. I'm also founder and CEO of the Quantum AI Foundation and the board member of QUBO and coordinator of QUBO. So these are some other quantum computing initiatives, quite similar to Quantum Association, I guess. So our goal is to support research, collaboration, and education in the domain of quantum computing and other new technologies. But today I will tell you about my research on solving vehicle routing problem using quantum annealing. And so first I will start by explaining adiabatic quantum computations and quantum annealing, because I guess that at least for some of you that may be a relatively new topic. And then I will tell you about the quantum annealing approach for route assignment. So this is an interesting approach developed by researchers from dwaves and Volkswagen about 3 years ago, but it can give you a good understanding of how quantum computing can be used in this domain. And later I will tell you about the algorithms, quantum annealing hybrid algorithms developed by me and my research team for solving the vehicle routing problem and its variants, such as capacitated vehicle routing problem or vehicle routing problem with time windows. Then I will tell you where to learn more about these approaches, about these algorithms. And at the end, hopefully we'll have time for the Q&A session, but feel free to ask your questions also during the lecture. So there is a dedicated Q&A chat where you can post your questions. And I will try to answer your questions, at least some of them, after each of these 4 parts of my presentation, because it might be easier to explain some details before going forward. So let's start from explaining the adiabatic quantum computations and quantum annealing. So first I will maybe start from explaining combinatorial optimization problems, because here I just listed some potential applications of quantum computing. In general, I guess that you probably know that quantum computing algorithms might be used, for example, in quantum cryptography to break some classical cryptography algorithms, or to develop quantum communication as well, or some even better cryptography methods. They can be also used for solving combinatorial optimization problems, which are which frequently occur in machine learning, artificial intelligence, finance, transport, logistics, and indeed quantum annealing and adiabatic quantum computations might be especially useful in this context. So they are designed to be useful for solving combinatorial optimization problems. That's why I emphasized this potential application of quantum computing. There might be also applications in sampling from difficult distributions, such as Boltzmann distribution, which also has applications in machine learning, or there might be applications in simulating quantum processes for discovering new materials or new drugs. But let's focus on combinatorial optimization problems. So what are these kind of problems? In combinatorial optimization problems, we basically search for the best of many possible combinations. So for example, we may want to answer the questions like, should I ship this package on this truck or the next one? Or what's the most efficient route a traveling salesperson should take to visit different cities, right? So these are just examples of combinatorial optimization problems. It turns out that physics can help solve these sorts of problems because we can frame them as energy minimization problems. And the fundamental rule of physics is that everything tends to seek a minimum energy state. So for example, objects slide down hills, hot things cool down over time. And this behavior is also true in the world of quantum physics and quantum computing, of course. So basically the goal now is to find a minimal energy state of a given quantum system, which represents our combinatorial optimization problem, which is encoded as an entanglement of qubits, right? So this might be a short summary of applications of quantum computing, or at least quantum annealing, to solve these kind of problems. Okay, so what exactly are the adiabatic quantum computations? It's good to first know what is an adiabatic process. So it's a process that does not involve the transfer of heat or matter into or out of a thermodynamic system. And in an adiabatic process, the energy is transferred to the surroundings only as work. So in case of adiabatic quantum computers, first a potentially complicated Hamiltonian is found whose ground state describes the solution to the problem of interest. So the Hamiltonian is basically a function which computes the energy for a given quantum system, for a given state of a quantum system. And next, this quantum system with a simple Hamiltonian is prepared and initialized to the ground state. And finally, this simple Hamiltonian is adiabatically evolved to the desired complicated Hamiltonian. And by the adiabatic theorem, the system remains in the ground state as long as it is the adiabatic process, of course. So at the end, the state of the system describes the solution to the problem. So this is a definition from Wikipedia. You can read more about adiabatic quantum computation. And it turns out that adiabatic quantum computing has been shown to be polynomially equivalent to conventional quantum computing in the circuit model. So for example, in approaches like Qiskit or other frameworks, you can basically solve similar problems, but usually it's not reasonable and efficient to just transform one approach to another. But in theory, it's possible. It's also good to know what might be time complexity of such algorithms and such adiabatic computations. And it looks that the time complexity depends on the minimum spectral gap of a given Hamiltonian for a given problem. And usually in case of difficult problems, such as NP-hard problems, this spectral gap, this minimum spectral gap is relatively low. So then the time complexity would be quite high, at least in theory. And in practice, it's even more difficult because in practice, in real world, we don't have real adiabatic quantum computers. Instead, we can use something that is called quantum annealing. So quantum annealing, again, starts from a quantum mechanical superposition of all possible states, which are our candidate states for the solution, with equal weights, so with equal probabilities. And then the system evolves following the time-dependent Schrödinger equation, which is a natural quantum mechanical evolution of physical systems. And then the amplitudes and the probabilities of obtaining given candidates keep changing, realizing quantum parallelism and according to the time-dependent strength of the transverse field, which causes quantum tunneling between states. And it will turn out that the quantum tunneling is also very important in this approach. And if the rate of change of the transverse field is slow enough, the system stays close to the ground state of the instantaneous Hamiltonian. But if the rate of change of the transverse field is accelerated, then the system may leave the ground state temporarily, but produce a higher likelihood of concluding in the ground state of the final problem Hamiltonian. And the transverse field is finally switched off, and the system is expected to have reached the ground state of the classical Icing model that corresponds to the solution to the original optimization problem that was just translated to our Icing model, to our quantum system. Yes, and as I said, because no real-world computation can be run in perfect isolation, then the quantum annealing may be thought of as the real-world counterpart of adiabatic quantum computing, which is a theoretical ideal, of course. So just to add some mathematics to explain even more clearly this approach. So basically, we have two Hamiltonians. The first Hamiltonian corresponds to the ground, to the initial state, to the initial quantum system that is easy to prepare. So it might be superposition of all possible states, for example. And usually this quantum system should be easy to prepare, right? And its ground state should be also easy to prepare. But we should also have another Hamiltonian and another quantum system, which might be much more complicated. And this Hamiltonian should correspond to our combinatorial optimization problem. And later in this lecture, I will explain how to transform our optimization problems to a specific Hamiltonian. But the important condition is that the ground state of this Hamiltonian, so the state with the minimum energy, should correspond to the optimum, the global optimum of our optimization problem. So that's the idea, right? And then if we change this value s, the value of our parameter s, slow enough, then the final state will be the solution of our problem. So initially, our quantum system is in a quantum state corresponding to the ground state of this relatively simple quantum system that is easy to prepare. But then when we apply a magnetic field, when we modify the strength of the magnetic field, then our system may evolve toward more difficult quantum system for which the ground state should correspond to a solution of our optimization problem, basically. So at least this is a theoretical idea, and according to this adiabatic theorem, if you change the value s low enough, then the final state will be the solution of our problem. So in practice, is difficult. So in practice, we can also change the strength of a magnetic field faster, and then we cannot be sure that we'll obtain the global minimum of our optimization problem, but we can still obtain a solution that might be good enough, that might be heuristically optimal, and when we repeat, or after repeating this procedure many times, it's likely that we'll get quite good solution to our problem anyway. And how it can be implemented in real world. So it's important. So I already mentioned about something like Icing model. So what exactly is Icing model? So the Icing model is a ferromagnetic model used in statistical mechanics. So we have variables which can represent spin up or spin down, and they correspond to states plus or minus one. We can think about them as atomic spins or magnetic dipole moments, for example, right? And then we have some relationships between the spins, which are represented by couplings. And we also have correlations or anti-correlations, right? And then when we define the Hamiltonian, so the function calculating the energy of a given quantum system for a given coupling between our atomic spins. And then the function can be expressed as an Icing model as follows. So we have our variables Si, Sj, and we also have parameters Hi and Ji again. So these are some linear coefficients corresponding to qubit biases, H, and the quadratic coefficients corresponding to coupling strengths, right? And S are just our variables +1 or -1, right? Yes, so now the idea is that if we can translate our optimization problem to a problem of optimizing such a mathematical function, so to finding values, assignments of values +1 or -1 to variables Si, Sj, then potentially we can use the quantum annealing to find the quantum state of our system that will correspond to the minimum energy state, which will again correspond to the global optimum, for example, or heuristically optimal solution of our optimization problem. So that's the idea. And when we define our Icing models, then it's good to also know what is the exact mathematical formulation of such a Hamiltonian, and it's called the quadratic unconstrained binary optimization, or QUBO in short. So it's very similar formulation to Icing model, as you can see. The only difference, in fact, is that these binary variables xi, xj may have the values 1 or 0, right? So now our goal is to find an assignment, the assignment of values to variables xi, xj that will minimize the value of a function f, right? And of course, our problem is now how to translate, how to transform our optimization problem to such a form, to such a QUBO formulation, to formulation of quadratic unconstrained binary optimization. So I will tell in the next part how to do it. I will show you two examples, but just to maybe tell a bit more what can happen later and what can happen in practice. So in practice, currently, we can run such computations, quantum annealing computations using a dwaves machine. So dwave is a company working on such quantum machines. It's a company from Canada. So here is a website from which I cite the description. So to begin with, there is just one valley with a single minimum. And then the quantum annealing process runs, the barrier is raised, and this turns the energy diagram into what is known a double well potential. So here is we have this double well potential. Here the low point on the left valley corresponds to the 0 state, and the low point on the right corresponds to the 1 state. The qubit ends up in one of these valleys at the end of the anneal. Right? So everything else being equal, the probability of the qubit ending in the 0 or the 1 state is equal as well. But we can control the probability of it falling into the 0 or the 1 state by applying an external magnetic field to the qubit. The field tilts the double well potential, increasing the probability of the qubit ending up in the lower well. Yeah, so this is a description from the dwaves website. So I recommend you to read more about this approach if you haven't heard about it before. An important thing is in this approach that we also take advantage of a quantum mechanics phenomenon that is called quantum tunneling, right? So when we modify the landscape of our function, of the function that we want to minimize, for example, then it may turn out that initially, so before the modification, the ground state, so the state with the minimum energy of our quantum system was here, for example, but after a modification, the global minimum will be in another place, in another location. So when we use classical computations and we use, for example, the gradient descent method, then it will not be possible to just go out from this valley here. But in quantum mechanics, thanks to this quantum tunneling process, it's possible that our system may evolve to another state for which the minimum energy state is in totally different place. So here we just take advantage of quantum mechanics. And now I will show you how we can potentially translate our optimization problem to this QUBO formulation that can be later solved using quantum annealing or adiabatic quantum computers. But before we proceed, I will check on our chat whether there are some questions. Let me check the Q&A. Yes, so there's a question. Quantum computing can deal with NP-hard like TSP. Yes, there are algorithms for solving a traveling salesman problem, which can be run on quantum computing, but it doesn't mean that we'll be able to obtain global solution in a reasonable time, right? So we still cannot be sure, because as I mentioned, if we want to be sure that our solution is a global optimum of TSP, for example, then we'll have to change the strength of this magnetic field slow enough. And I showed the slide with the time complexity of these computations, right? So it depends on the minimum spectral gap of the Hamiltonian. And it turns out that in case of NP-hard problems, this minimum spectral gap is relatively small, right? So there are small differences between solutions. Yes, so between solutions that are very close to global optimum. How slow is slow enough in practice? So as far as I heard, in practice, it would be very slow. So there will be no advantage comparing to classical computers. But at least this is what I heard. But in practice, we even don't have the adiabatic quantum computers, as I mentioned. Instead of adiabatic quantum computing, we have the quantum annealing, in which we just change the value of the magnetic, the strength of the magnetic field faster. But because of that, we cannot be sure that we achieve global minimum, but it's still possible that we'll obtain relatively good solution. So most likely it will not be a global optimum of our problem, but it's still quite likely that it will be reasonable solution. And in such cases, in such cases we can achieve quite good results. I will show you soon an example of real-world applications. It will be based on a research presented by scientists from dwave and Volkswagen. And in their paper, they also mention what's the real-world time and what was the real time that they needed to obtain a relatively good solution. Okay, so yeah, I already answered this question. So let's start talking about this real-world application, one of the potential real-world applications. So this is based on the paper Traffic Flow Optimization using a Quantum Annealer. So here you can see the title, and here's a link to the original paper. I recommend you to read it because it's relatively short, and I think that also it's relatively easy to understand. Okay, so basically the scientists from Volkswagen and dwave tried to use quantum annealing for traffic flow optimization. So for finding good routes of taxis in Beijing, taxis traveling from the city center in Beijing to the airport. And they built a road network, a real road network from OpenStreetMap service, as far as I remember, and they had routes from real GPS data. So the data set is called T-Drive, and indeed it was a data set with real data from real taxis in Beijing, right? So thanks to that, they had information about real routes selected by taxis in Beijing. But for each taxi, for each car, they added two possible routes between source and destinations, right? So they also assumed that our algorithms may just select one route from three possible routes. So in the set of three possible routes, we have two artificial routes that were added by researchers and one route that was used by the taxi in a real world in Beijing. And cars may share road segments, and they also introduce an assumption that travel time is proportional to the function, which is a square of a number of cars on a route. So in fact, it's a huge simplification because normally it doesn't have to be just a square relation, but in some regimes, in some range of traffic densities, it's relatively close to the square function indeed. But also another simplification is that they assume that all the cars will pass a given road segment at the same time. So all cars passing a given road segment during the simulation. So this is a simplification, but thanks to such a simplification, they were able to build very nice, very elegant solution using dwave's machine and using quantum annealing. And of course, the goal was to minimize the total travel time of all cars, right? So let's introduce notation. We have binary variables qij, which may take values 0 or 1. So the value 1 means that the car I takes route j. And if in a given solution, the car I doesn't take route j, then the value of this variable qij should be equal to 0. So it's necessary to introduce such a constraint, right? So basically this constraint means that for each car, so for each value I, for each car should select exactly one route, one from the set of three possible routes, right? So only one from these three variables, qi1 to 3, should be equal to 1, and the two other variables should be equal to 0, right? So in only such a case, this this function, this expression is equal to 0, right? So this is just to ensure that each car selects only one route, and it's just equivalent to such an expression, right? So we have the equation that 0 is equal to some function of binary variables qi 1, 2, and 3, and we should just have it for each car, right? And then let's also introduce another notation. BS is a set of these binary variables qij which are associated with routes that share street segment S, right? And then the cost of traveling through this road segment is just equal to the square of the number of cars passing given road segment. So this is just based on the assumption that they introduced, right? So I told you that this is a simplification, but it's quite reasonable assumption as well, right? So this is a cost of traveling through this road segment. And then we have an objective function, which is just a sum of all costs for all road segments in our road network. Plus, we add a constraint. We add a constraint. So this was our constraint for a single vehicle, for vehicle I. And then we just calculate the sum for all vehicles, right? So that would be a cost of not fulfilling the requirement that each car selects exactly one route. So, and then if we set the value of the parameter lambda large enough, then and then we apply our solver and we want to find the global minimum of our objective function, then it will turn out that in any such a solution, or for any such a solution, this part should be equal to 0, because the value of lambda was so large that if this part is not equal to 0, then this component will dominate the whole sum. And for such a solution, it cannot be a global optimum. It cannot be a solution for our optimization problem, right? So thanks to just using large value of parameter lambda, we can ensure that in each solution found by our solvers, this condition will be satisfied for each vehicle, right? And then at the same time, we want to minimize the sum of all costs for all road segments, assuming that all the specific conditions are satisfied, right? So this is the Cubo formulation, the objective function that they introduced, and you can easily see that this is a Cubo formulation. So this is a quadratic binary optimization problem because we have binary variables, and each variable in this objective function is or appears only with a power of 1 or power of 2 at most, right? So this is a quadratic optimization problem, and it's also quadratic binary optimization because all our variables are binary variables. All right, so that was a Cubo formulation, and as I explained, we can translate this Cubo formulation to a corresponding Icing model, which will represent a given a state or Hamiltonian of a given quantum system. And this Hamiltonian should be a Hamiltonian in the quantum annealing formulation, which I introduced in the first part, so that we can try to solve this problem using quantum annealing on D-Wave. And indeed, the researchers from D-Wave and Volkswagen conducted such a research on D-Wave 2X quantum processing unit, and that's the result. So they had 418 cars. So in total, there were more than 1,000 logical variables. So 418 times 3 routes. So in total, we had 1,254 binary variables and 3 to the power of 418 possible solutions, right? Because for each of the 418 cars, we may select one of the 3 possible solutions. So that's the size of a space of possible solutions. So it's an astronomical number, of course. So we cannot just check all the possible solutions. And we can try to apply some smarter algorithms, some meta heuristics, for example, to find a good solution on classical computers. But as I explained, we can also use quantum annealing to solve it. And it turned out that as a result, after about 22 seconds of computations, so this is the answer to the question, how long should be this slow enough in practice. So in fact, we cannot find a global optimum, but it was sufficient here to run computations for 22 seconds to find a solution that was relatively good. So on the left, in the left figure, you may see the real world traffic from Beijing, and the color corresponds to the traffic density, so number of cars traveling through a given road segment, right? So I guess that most or each or most of these 418 cars, 418 taxis, has just selected a single straight route, and because of that, there was a huge traffic jam. So of course, the researchers also assumed, I guess, that there were no other cars in the road network, which is also a simplification. But after applying quantum annealing, they were able to find another assignment of routes for which the traffic density and also travel times were lower. So the solution was better. So unfortunately, there was no comparison with classical algorithms. So we cannot say that we will not be able to find such a solution on classical algorithms, and most likely will be able to find similarly good or maybe even better solutions using classical algorithms, and probably also faster. So this is what I expect based on some other experiences with the current quantum annealing machines, quantum algorithms. But anyway, it shows that we can develop quite interesting and relatively simple quantum annealing algorithms for a real world problem, right? So this is a real world problem. This is an example of a real world problem. And in fact, I heard that dwave has implemented such an approach together with Volkswagen in Lisbon to manage the vehicles of the public transport, I guess, in Lisbon, in Portugal, for purpose of transporting attendees of the conference, as far as I remember. But later at the end, I will also present a link to the article which describes this application in Lisbon in details. All right, let me now try to answer some other questions, because I see that more questions has appeared on our chat. Yes. There is a suggest reading for entropy example for quantum tunneling. Can we have the web links or the presentation itself? Yes, of course, I can share my slides later, no problem. Yes, and there is also a comment that the solution is also similar to Vasin's scheduling event presented here 2 weeks ago. Yeah, 2 events ago. That's interesting. That's true. Both scheduling algorithms are using quantum annealing. Great. And then if all cars were self-driving plus coordinated, this would be a great way to optimize the entire city's traffic grid. I agree, because if we don't have self-driving cars, then we cannot be sure that our drivers will follow the proposed routes. But indeed, when we have self-driving cars, when we have only autonomous fleet, then we can potentially manage the fleet in an optimal way. So I agree that this approach might be especially interesting and especially useful in the world with self-driving cars only. Yes, and there is also a comment that yes and no, so it's a quantum state of the answer, because extra variables could saturate or space explosion and extra variables. So I'm not sure to which approach is related, but anyway, we can elaborate it in details later during the Q&A session. Okay, do we have any more comments? How long might it take an estimate maybe to get a global minimum if we were to do it on a quantum annealer? So as I said, unfortunately, when we use a quantum annealer and not adiabatic quantum computer, we cannot be sure that we'll obtain a global minimum, right? So the global minimum, or getting a global minimum, can be ensured only when we have a real adiabatic quantum computer. But I explained that in the real world, there are no real adiabatic processes. At least I'm not aware of such real adiabatic processes. So in fact, as far as I know and as far as I understand, in the real world, we cannot be sure that we'll obtain a global minimum, and it really doesn't matter how long we run our computations. So it's not just a matter of time, because this adiabatic quantum computing model is rather a theoretical model, but in the real world, we just cannot apply it. And another question, what does lambda represent and why is it too high? So the lambda, so as I said here, we should set the value of lambda to be relatively high, because we want this, the second component of this sum, to be equal to 0 in any optimal solution found by our solver, right? So this is our objective function here, right, at the right bottom. So our solvers, our quantum annealers, will find relatively good solutions for this objective function. But in such a solution, we want to have this sum equal to 0. Because otherwise, the condition that is above, the condition that each car takes exactly one route, will not be satisfied. So it will not be a real world solution, right? So that's why we should set the value of lambda to be relatively high, to ensure that if the second component is not equal to 0, so it should be greater than 0, because we have the power of 2 here, right? So it cannot be negative. Then if, for example, the value of the sum is equal to 1, then due to the high value of lambda, it just cannot be a solution found by our solver, because there will be some other solutions for which the sum is equal to 0. Maybe the cost is a bit higher, but that would be a realistic real-world solution to our problem, right? So the value of lambda should be set to be high enough to ensure that in each solution found by our optimizers, by our solvers, the condition that each car selects exactly one route is satisfied. So that's the reason why we should set the value of lambda to be high enough. All right, and now I will go to, because so far I've presented the research introduced by scientists from dwave and Volkswagen, and now I'll tell you about some algorithms developed by me and my team. So these are the algorithms for solving the vehicle routing problem. But I hope that the approach from dwave, which I introduced, will help you in understanding our algorithms as well, because our algorithms are a bit more complicated, I would say, because also the optimization problem is more difficult. But thanks to understanding the previous algorithm, I believe that it would be easier for you to understand our approach as well. All right, so let's start by defining the vehicle routing problem. So in the vehicle routing problem and its variants, we have a directed graph with non-negative costs assigned to edges, and that's our input. And we may have different variants of the vehicle routing problem. So for example, in TSP, in the traveling salesman problem, we have n selected vertices in the graph, which can be our customers, for example. And now the question is, what's the shortest possible route that visits all of them, all of these n vertices, all customers, and returns to the origin vertex, which is our depot. The vehicle routing problem is a generalization of TSP, because we also have n selected vertices in the graph, which are our customers, but we also have m vehicles located in the depot. So here in TSP we have only one vehicle, but in the VRP we may have more than one vehicle, right? So we have m vehicles located in the depot. And now the question is, what's the optimal, so with minimal cost, set of up to m routes, which in total visit all the selected vertices and start and end in the depot. So again, we want to start and end in the depot, and we may use up to m vehicles to just visit all our customers, right? Because you can think about it as delivering some products when we have an e-commerce service, right? So we want to just deliver something on time to our customers. But there might be even more realistic variants, like capacitated vehicle routing problem, in which we also assume that there are some bounded capacities of vehicles, right? And we may also add time windows, right? So we may have bounded capacities of vehicles and also time windows in which our customers want to be served by our cars, by our fleet. And all these problems are NP hard. So the NP hardness of VRP and its variance can be easily proved thanks to the NP hardness of TSP. And how to solve it? How to solve it using quantum annealing? Because there are also some classical algorithms, but now we want to solve it using quantum computing and quantum annealing. So again, we have to introduce our notation. So let's assume that we have a set of our trucks, vehicles, and these are just identifiers. The set T is a set of identifiers for our vehicles from 1 to m. We also have identifiers of vertices or nodes from 1 to n plus 1. So n plus 1 is a depot. So as I said, we want to start and end in the depot, for example, in our magazine. And 1, 2, 3 up to n are our customers. And Cij is a cost of travel from node I to node j in our graph. Yeah, and Cii is equal to 0, right? So there's no cost related to just staying in the same place. Qijk is a binary variable. So it's a binary variable that should be equal to 1 if and only if in a given setting, the vehicle I visits the node j as kth location on its route. Otherwise, it should be equal to 0. All right, so again, I is from the set of identifiers of vehicles, j is from the set of identifiers of our vertices, our nodes, and k is from the set from 0 to n plus 1, because that's the order, right? So in total, we may visit up to n customers, but also the depot should be at the first place, and depot should be our last visited node. So that's why in total we have, and we may have up to n plus 2 different identifiers here, right? And it's good to do some observations. So the first observation is that for each vehicle I, all the binary variables xi, n plus 1, 0 should be equal to 1, which means that we start from the depot, right? So for each vehicle, n plus 1 is our depot, and 0 is just the first position on our route for vehicle I. So this variable should be equal to 1, because it means that we always start in the initial location. And for all other values, so for our customers, when j is lower than n plus 1, so 1, 2, 3, or n, so these are identifiers of our customers, this value of this binary variable should be equal to 0. So it means it's equivalent to saying that the depot is always the initial location on each route. And also it should be the same for the depot in case of the last location. So if xi n plus 1 l is equal to 1 for some value l, and again for each vehicle I, n plus 1 is a depot, then for each indices greater than l, xijw should be equal to 0 for our customers. So and it should be equal to 1 when j is equal to n plus 1. So basically it means that the depot is always the last location on each route for each cars, and each car just stays in the depot after reaching it, right? So it means that if we visit the depot at some point in time, which is denoted as L, then for all other points, all such variables where j represents our customer should be equal to 0. So when we visit the depot, then we just stay there, and that's why the binary variables corresponding to the depot should be equal to 1. So I guess that it might be a bit difficult to understand when you see it for the first time, but indeed it's a bit complicated. But don't worry, I will just try to give you some intuitions how to use it in practice. And you can find the details in a research paper that we published last year. So this is a part of the Cubo formulation for our problem. So again, it may look very complex, but just to give you the intuition, you don't have to understand this formula or at least everything, but just to give you an intuition. We have three components in this sum C, right? So the C is the cost that we want to minimize. We want to minimize the cost of visiting all the customers, right? And we have three components of this cost. And the first component is just a sum of all costs of travels from the depot to the first visited node. It's just the first section of each car's route. The second component is a cost of the last section of a route, of a section leading to a depot in which we just stay after visiting some other customers. In a special case when a single car serves all n orders. And only in such a case this component can be greater than 0. So you can check it, you can verify it. And the last part is the cost of all other sections of routes. So I guess that usually it may take, so people may need about a few minutes to understand why why it's true. But as I said, you can also find the details in our research papers. But just as for now, I think it's sufficient to just know that we can define the cost of our solution, of our route assignment, as a sum of some other components, which again, as you can see, contain our binary variables x in a power at most 2, right? So here we have power of 1, here we have power of 1, and in the last component there might be the power of 2, there might be square, for example, right? So again, it looks that this is a quadratic binary formula again, and indeed we'll use it to define our Cubo formulation. But before we do it, we have to introduce another component to our sum, which is similar to this component corresponding to the constraint developed by researchers from dwave. So let's think about a binary function of n variables y. And it's easy to see, so these are just binary variables. It's easy to see that the minimum value of this function is equal to -1, and this value can be achieved only if exactly one of these binary variables is equal to 1. Yes, then this square is equal to 0, and the minimum is -1. And we can use it to just define the Cubo formulation corresponding to the required constraints here. So here we have our function a. So this is the function that we just introduced, the function of n variables. And again, we have a function of some number of binary variables, and these are just our binary variables corresponding to our vehicles, our nodes, right? And again, you don't have to understand it in details, but just to give you an intuition, this part, so the first part of the sum, correspond to the condition that each delivery is served by exactly one vehicle, right? Because here, as you can see, we just have a sum of different indices for our customers, right? And here the given index, the given value k is just constant, right? So we may modify our vehicles, and we may modify the orders of visiting a given customer, but exactly one of these variables can be equal to 1 in order to have this constraint minimum, right? And the second component corresponds to the constraint that each vehicle is in exactly one place at a given time. So again, you can check that only if such a condition is satisfied, this function will achieve a minimum. The sum will achieve a minimum. And then, in analogy to what researchers from dwave and Volkswagen did, we can define a Cubo formulation, which is a combination of the two components that we introduced. The C, which is this complex cost that you can see here, and the Q, which is just a constraint, which that should be satisfied. And again, for some constant, so in this case, we should set the value of the parameter A2 to be large enough to ensure that in an optimal solution found by our solver, this function Q will reach its minimum. So that's the motivation, and for such cases, we want to minimize our cost. So this first component. All right. So now how to do it? So we developed four hybrid algorithms. In fact, so this is the basic QUBO formulation that we used, and we just called it full QUBO solver, or FQS in short. But we can decrease the number of variables, because you can see that in this QUBO formulation we had many binary variables, but we can decrease the number of variables for each vehicle by assuming that every vehicle serves approximately the same number of orders. So up to A plus L deliveries, where A is the total number of orders divided by the number of vehicles. So this is the average number of orders per vehicle. And L is a parameter that we can call a limit radius, which controls the number of orders. So in practice, we usually want our fleet to be evenly loaded, basically, right? So to have more or less the same number of orders served by each vehicle. So this is a realistic assumption, and thanks to that, we can significantly reduce the number of binary variables. So thanks to that, we can solve larger instances of our vehicle routing problem, right? We can also develop another approach, which is even more hybrid, and we called it dbScan solver because it uses a classical algorithm for clustering that's called recursive dbScan. So in the recursive dbScan algorithm, we basically try to cluster points that are relatively close. So if we have a given cluster, and if a new cluster is close to any point from another cluster, then we just merge these two clusters, basically, right? So that's the idea behind dbScan, and it's just important to set the value of this closeness properly, right? So after clustering, we can, after clustering the instance of our solution, so after clustering all our customers, or the locations of our customers, we can apply the traveling salesman problem for each of the clusters, right? And we can solve this TSP using the full QUBO solver that we've developed, right? Because we can just assume that in each cluster, or each cluster is served by exactly one vehicle. So then we can just solve TSP in this cluster. So if the number of clusters is equal to or is lower than the number of vehicles, then the answer is no immediately. But otherwise, the solver runs recursively, considering clusters as new deliveries, so that each cluster contains orders which in the final result are served one after another without leaving the cluster. And we also concluded that by limiting the total sum of weights of deliveries in cluster, this algorithm can solve the capacitated vehicle routing problem if all capacities of vehicles are equal, right? So if we have bounded capacities, but capacities are equal, then we can also use this dbScan solver to solve the capacitated vehicle routing problem. And it's also quite realistic to assume that in our fleet of vehicles, all the vehicles are the same and have the same capacities, right? So it's not something very strange. All right, so that was the third algorithm, and now the fourth algorithm, that's the most advanced. We called it SPS, solution partitioning solver. So in this approach, we first try to solve. So again, this is a hybrid algorithm in which we apply the quantum algorithm first, and then apply a classical part. So first we apply one of our quantum algorithms described earlier. So for example, the first QUBO solver, that was our first algorithm, to just solve an instance of the traveling salesman problem. So let's assume for now that we use only one vehicle to just visit all our customers, right? So in the real world, in practice, it will not be possible, but we'll show you how we can modify such a solution of TSP to just use more vehicles. Yes, so first we solve the instance of TSP, the instance of traveling salesman problem. And then we just divide the solution into consecutive intervals, which then can be considered as solution for the capacitated vehicle routing problem. And now how to divide the solution of TSP into such clusters, because in each cluster, we would like to have the limited or bounded sum of weights of the orders that we have to deliver, of the products that we have to deliver, right? So this is one of the requirements, one of the conditions for our clusters. And also the number of clusters cannot be larger than the number of vehicles that we have. Okay, so let's assume that D1, Dn is the TSP solution for n orders. So again, we have n customers, and we apply our quantum algorithm, or it can be also a classical algorithm solving TSP, right? And then we just get a solution. So this is a sequence of the visits that we should perform, right? D1 up to Dn. So this is a solution, and let's assume that PV is a capacity of the vehicle V, and also let's assume that Wij is a sum of weights of orders from Di to Dj in this order corresponding to the TSP solution, right? So this is a sum of weights of these orders. And also let the cost Ij be the total cost of serving only orders from Di to Dj. And another notation, dPIS, is a cost of the best solution for orders from D1 to Di. So the I is indexed here, and for the set of vehicles S. And now we can apply dynamic programming to just solve greater and greater instances of CVRP. Assuming that we can solve, or we have good solutions for the values j that are not greater than I, right? So for a subset of our customers in the TSP solution, but without one vehicle, without vehicle V, right? So this is the optimal cost for serving these customers without vehicle V. And then we just assume that our vehicle V serves all the other customers from j plus 1 to I. And this is the cost of serving these customers, right? And we just want to find the minimum cost for all the, assuming that we just try to remove different vehicles V. And we also consider different values of j as starting points, starting customers for this vehicle V. So basically, that's the logic behind this dynamic programming formulation. So this is just a classical part that we solve using classical computer. But we can see that the time complexity of this solution will be relatively large because of the number of subsets, right? So that might be quite expensive. But we can apply a heuristic. Instead of having the set of vehicles, we may consider that we have a sequence of vehicles. So again, if the vehicles are the same, so if they have the same capacity, then it's not important. So the sequence is the same as having a sequence is the same as having a set of vehicles, right? And otherwise, it will be just a heuristic, but it's still reasonable. And we just assume that we attach them to deliveries in such an order from this sequence. And then instead of just checking all the possible subsets, we just check only one subset in which we just remove one of the vehicles, right? And we can check that thanks to, so that this equation holds. So this is a difference between consecutive values of the formula in the brackets for different values of I. And so there's a difference between I minus 1 and I, as you can see. It can be easily computed in a linear time because it just depends on the cost. cost of traveling from I minus 1 to I, and from I to n plus 1, and from I minus 1 to n plus 1, right? So this is relatively simple. We can just compute it in constant time. And thanks to that, we can also efficiently solve this dynamic programming formula in a linear time, and then our solution is efficient again. So that was a hybrid algorithm in which we used quantum annealing only for solving the TSP instance at the beginning, and then the TSP instance was just divided into different clusters using dynamic programming formula. So that's the idea behind this algorithm. All right, and that was the last part containing quite maybe complex math. It's hard to say. So it's I guess that it's relatively simple math, but we have just many variables here, and that may make it a bit difficult to understand. But now I will tell you a bit more about the results. So our goal was to compare the results of different algorithms, quantum and classical algorithms, on several data sets, because we wanted to compare our quantum or hybrid algorithms with classical algorithms, which are well established in the scientific literature. So for example, in case of classical algorithms, we tested simulated annealing, B algorithm, evolutionary annealing, and DB scan with simulated annealing. These are algorithms, classical algorithms, that can be found in research articles concerning the vehicle routing problem. So these algorithms are well established in a scientific community. And our quantum or hybrid algorithms were run using dwaves Leap platform and using two solvers. So the QB solve, which can be run on a quantum processing unit, or it can we can just run a simulation on CPU, or we can also run a hybrid solver, which uses QPU and CPU at the same time. We also prepared several datasets. So the first dataset was a standard benchmark dataset for capacitated vehicle routing problems, which is also well known and frequently studied by the scientific community. And we also used a dataset built by us based on a realistic road network of Belgium, close to Brussels. And this dataset was acquired from the OpenStreetMap service, and it contained 51 tests. So why Brussels? So in this research, we collaborated with one company from Belgium that was interested in this approach, and because they also had earlier started last mile delivery service in Brussels. So that was the reason why we used a realistic road network of Belgium. And yeah, so this is the description of this Christofides standard benchmark data set. So if you look for a scientific literature on vehicle routing problem or its capacitated version, then you will see that many articles just compare the algorithms on this standard benchmark data set. So this is a standard in this research area. So as I said, in case of the dataset built by us based on a real road network of Belgium, we had 51 tests with different number of orders and also different locations of orders and the depots. So in some cases we had relatively low number of orders. In some cases we've had even more than 100 orders. So these are the results on the smallest data sets. So initially we tried to use our full QUBO solver only on the quantum processing unit, but it turned out quite fast that unfortunately when the quantum processing unit is not able to just solve our QUBO formulation even for 3 vehicles, or for some instances even for 2 vehicles, there are difficulties, right? So currently this problem is too difficult, or our algorithms are not suitable for quantum processing units. But instead we can run our algorithm, or we can use the hybrid solver. And in case of hybrid solver, we are able to achieve even better results than in case of simulating the quantum solver on CPU. So in case of hybrid solver, as I said, the part of the computations is just run on a quantum processing unit and part on a classical CPU. We compared the results from this full QUBO solver, that was our first algorithm, with the results from average partitioning solver for CPU and for hybrid. So it turns out that for small instances, FQS of full QUBO solver might be maybe even better. Here is the better result, but in general, the results are similar. And later we checked the same algorithms for larger data sets with more orders. And for more orders, we observed that this average partitioning solver was able to outperform our full QUBO solver in several cases. So when we have more than one vehicle, then usually the average partitioning solver gave us better results. And DBSCAN solver had similar or a bit worse results. So still APS was a relatively good algorithm, and still on a CPU we are able to achieve a bit better results than in case of hybrid approach, but there were also cases in which using the hybrid processing unit gave us an advantage. So later we ran our experiments on the largest data sets. And for the largest data sets, it turned out that the DBSCAN solver outperformed our average partitioning solver significantly. So these are the costs, the optimal cost found by our solvers. So it looks that for largest instances, the DBSCAN solver run on CPU, so it was a simulation of quantum annealing, in fact, achieved better results comparing to average partitioning solver. And finally, we compared this DBSCAN solver with solution partitioning solver, with the last solver on the largest data set, where we had 2, 3, 5 vehicles and capacities, also limited capacities, and also more than 100 orders. And it turned out that in most cases, this last algorithm, solution partitioning solver, was able to found better results comparing to DBSCAN solver. So finally, we also compared this solution partitioning solver with the classical algorithms, with 3 classical algorithms, also on our data set. So on this real-world data set for the road network of Belgium, the results of this hybrid, because in this case it was a hybrid solver used, the results were a bit worse, but still comparable to classical algorithms. The evolution annealing algorithm was probably the best, significantly better than other classical algorithms, and better than solution partitioning solver, which is our hybrid algorithm. But when you run similar experiments on this benchmark data set, Christofides data set, it turned out that this solution partitioning solver was able to outperform simulated annealing and B algorithm on several instances. It was so the results were worse in case of than in case of DBSCAN solver, DBSCAN algorithm with simulated annealing. Yeah, DBSCAN with simulated annealing. Sorry. So it seems that this DBSA classical algorithm was probably best, or was quite good in most of the cases, but in some cases it was also not able to find any solution for our problem. But anyway, this hybrid algorithm, solution partitioning solver, as you can see, was able to get comparable results to classical algorithms anyway, right? So in some cases, the results were even significantly better than in case of some classical algorithms. But we cannot say that in general, the results were better. All right, so some conclusions from this experiment. So first of all, it doesn't make sense to run experiments only on quantum processing units for large test cases. So the quantum processor, quantum solver was not able to find good solutions. So we had to use hybrid solver, so run some computations on quantum processor and some on classical processor, and in such cases we are able to just achieve quite good results. And it looks that this solution partitioning solver gives the best results among quantum algorithms, we also compared it with some classical meta-heuristic, but compared it this time on a quantum solver. And it usually gives a bit worse results, but sometimes the results are better comparing to some classical algorithms. All right, some plans for the future. We want to develop our algorithms further in order to solve the extension of CVRP, so capacitated vehicle routing problem with time windows, and maybe also some other variants of VRP. To investigate for which scenarios the hybrid algorithms give the best results comparing to classical algorithms. So for which scenarios we may expect some advantages, because we believe that there might be also some properties of the road network or the instance of the problem that may make the problem a bit more difficult or a bit more easier for quantum algorithms, comparing to classical algorithms at least. Yeah, we also want to investigate some algorithms, quantum algorithms for solving CVRP-TV using circuit-based quantum computers. So when we want to use quantum programming frameworks like Qiskit, for example, or Rigetti, then we have this circuit-based approach, which is another approach for quantum computing. It's different than quantum annealing. So I explained that these approaches are polynomially equivalent, but they are not the same. And there also exist algorithms for solving such problems using circuit-based quantum computers as well. So at the end, I want to mention that this research the presented work, this presentation is based on the article New Hybrid Quantum Annealing Algorithms for Solving Vehicle Routing Problem, and was presented at the ICCS 2020 conference. So I would also like to thank the other co-authors, because there were 9 authors in total. So I would not be able to just run all the experiments by myself, of course. So here are some links to our publication if you are interested as well. This research was also carried out within the frame of the Green Last Mile Delivery project, which we realized at the University of Warsaw, but with the project partners. Coloroid Group, so that was our partner from Belgium. That's why we run experiments in the road network of Belgium. University of Cambridge from the UK, and Technion from Israel. And the project was supported by EIT Food, which is just an European initiative to support innovations in the food sector, in fact, because initially we were just focusing on optimizing the last mile delivery of food products. So that's why we just carried out this research within the EIT Food, or with the EIT Food support. All right, now I can tell you where you can learn more, when you can read more about these approaches. But I can see that there are some questions. There are some questions on the chat. So will you share the paper links mentioned? Yes, I can share them, of course. Notation D for destination weights for each is a bit confusing, I guess. So yeah, as I said, it might look difficult, but so that's why, as I said, it's better to just read our paper, and then based on that, when you start thinking about it, you can understand deeper why it's correct. Yeah. Yes, now it's the same. Okay, please describe the clusters again in relation to deliveries. So I will just come back to this topic. And you thought of this non-annealer such as IBM. So yeah, as I said, so this is in our future plans, right? To just do it using the circuit-based models for quantum computing. What's the barrier keeping pure QPU algorithms for finding solution in these cases? So one of the barriers is the number of binary variables. So the number of binary variables is large, and in the quantum annealer from D-Wave, we only had about 2,000. We only had about 2,048 qubits. Now in the newest platform from D-Wave, we have more than 5,000 qubits, right? But in the platform, but this advantage platform was released about four months ago, and in 2019 we had only access to the machine with about 2,000 qubits. So this is one of this is one of the limitations, of course, that when we have large number of these binary variables, then each binary variable has to be represented as a separate qubit. So this is one of the limitations. Another limitation is that in general, so I don't know how exactly dwaves machine work inside, because there are some controversies regarding this machine. Some people say that it's not a real quantum computer, and yeah, as I said, so adiabatic quantum computations can be equivalent to circuit-based models, but in case of this quantum annealer, I believe that indeed it's something totally different than circuit-based quantum computing. And I guess that there might be also some internal limitations, so that the solver was just not able to find the solutions. Maybe that was indeed due to the number of qubits. And another thing is that this quantum annealer had about 2000 physical qubits. But it's possible that there are also maybe some error correction codes, as in case of circuit-based models. I'm not sure, but it would mean that in fact we have even a lower number of logical qubits. So this is something that I would expect, but I don't know why. So I don't know how exactly dwaves machine works inside. So I cannot be sure what was the reason that this QPU alone was not able to just found solutions for larger instances. Can you please some TSP solving method on IBM experience? There are some research papers on that. And there is, so yeah, I don't have any links here, but you can easily find. And if you check our research paper, to which I gave a link, we also mentioned about such TSP approaches in some other research papers. So there is extensive related works part, and we just give references to the bibliography with papers describing also this more circuit-based approaches, which can be implemented on IBM experience. But I'm not sure if there's any such implementation available online as an open source, for example. Is there a GitHub for this? Yes, there is a GitHub. I can share a link later together with the slides. +1 for GitHub repo. Okay, awesome presentation. Thank you. Excellent presentation from beginning to end. All aspects very nicely explained. Thank you very much. Does each algorithm run on multiple CPUs or QPUs? I think that it was run only on a single CPU, but I'm not sure, because it was run in a dwaves cloud using this dwaves sleep framework. So I'm not sure how many CPUs or QPUs do they use internally. So it was for us, it was not available, I guess. For starting a quantum annealing process, does it make any difference if a fairly good approximation of the optimum is already known? It might have been calculated by some heuristic algorithm. It's a very good question. To be honest, so the only difference is that we would have to somehow prepare this quantum state, right? And now the question is whether we can prepare the state. If we can prepare such a quantum state corresponding to this fairly good approximation, fairly good solution, then potentially we can start. And now the question whether it will help us, it's hard to say, because I think that I would expect that ultimately the solution will be, or eventually the solution will be probably very similar, because thanks to this quantum tunneling approach, quantum tunneling phenomenon, we can also just jump to some other heuristically good solutions, right? So I think that it's probably not that important, but I guess that it might maybe speed up some experiments. It may accelerate some computations, maybe. So there might be some advantages in terms of time of computations, but I doubt that there will be advantages in terms of the quality of solution. Can you pass the links in the chat? I can do that later after I stop sharing my slides. And as I said, I can also share my slides later, and there are all the links. Thank you for interesting and clear presentation. I learned a lot. Great, thank you. And how do you choose the capacity for each test? I saw different number of capacities, like 40, 50, 60. why don't you use the same capacity for all tests? Because we wanted to test different capacities and also to check what will be the outcomes for different different capacities as well, right? And what are the limitations? Because we observed earlier that if we, for example, increase the number of orders or the number of vehicles, then at least this initial quantum algorithms or our quantum solvers are not able to find good solutions, right? So we are also curious whether there might be some differences when we also modify the capacities, the values for capacities, right? And as I mentioned, so this is part of our future plans that we want to investigate for which scenarios, so maybe also for which capacities these hybrid algorithms give the best results comparing to classical algorithms, because it's possible that for some instances of our problem, the classical algorithm, the quantum algorithms may give results that are much closer to the results of best classical algorithms than in a general approach, right? So that may be also just due to the representation of our solutions, of our instances using qubits. All right, there are some other questions. Is there a good place to follow further developments? Yes, so I will share links after the presentation. The question from Helen: how do you choose the capacities? Okay, so I already answered that. So, I guess that maybe not exactly randomly, but we just wanted to just set the values that would be reasonable, right? And I also explained why we just didn't use the same capacity. We just wanted to investigate what might be the differences in the results when we modify the number of vehicles, the number of orders, and the capacities as well. All right. So I think that was the last question, probably. There are also some questions in the Q&A. There is a question: consider adiabatic slow change of more than one physical parameter, such as temperature. I don't know, so it's rather a question to people from D-Wave. So you can ask a person from D-Wave on Monday. So soon I will present, and I will invite you to attend another webinar which I organize on Monday. And there will be a speaker from D-Wave, so you can ask by yourself, of course. And for the taxi's route optimization, does it specify the destination for each taxi? Yes, so the destination was the same each time. So as I said, each taxi traveled from a city center in Beijing to the airport, right? So the start point and the destination was the same each time. We just only had the option to just choose different routes for given taxi. For starting a quantum annealing process, does it make any difference? Okay, so this question has already been posted and answers. What about computing time comparison among the solvers? So to be honest, we didn't measure the exact computing time, because so it was not easy, in fact, to just implement it. So we just didn't compare it. But there are also the classical components involved. So anyway, as far as I remember, the time was also comparable to classical algorithm. This is the only thing I can say for now. Are the quantum and hybrid algorithms run in parallel? No. So we just run different experiments sequentially. So I'm not sure if that's the question, but I'm not sure if there was even an opportunity to run several experiments at the same time. So we ran them sequentially, so one after another. But within a single run, I'm not sure if there were several QPUs and several CPUs in use by the solver. Probably not. All right. Okay, so where will the links? Yeah, there are questions about the links. So of course I will share my slides. Yes, so maybe let me Yes, I will post the slides on the website, no problem. And regarding the event, where to learn more. So I would like to invite you to attend also the remote-only episode 24 of the Warsaw Quantum Computing Group meetings. So this is a similar meetup that they organize in Poland, in Warsaw. And the next meeting will be on Monday. The speaker will be Victoria Golliber from D-Wave. She is a researcher from D-Wave, and she will tell about the advantage, the latest generation system from D-Wave. So in fact, this is, as I said, this more powerful quantum annealer developed and released by D-Wave a couple of months ago. So you can find more information on the website of this meeting, and there is also Google Forms to register, so you will also have access to the slides. There are also some other useful links, a link to the D-Wave's website, D-Wave's YouTube channel. There are very nice presentations about this quantum annealing approach. Here is the link to this paper from the scientists from D-Wave and Volkswagen. And here is an article about implementation of this approach from D-Wave and Volkswagen in Lisbon, as far as I remember. All right, I'm not sure if there are any more questions, and if we have time to answer. Yeah, so there are only the questions about the links. So maybe in that case, maybe I will just stop sharing my slides, and I will try to copy and paste the links here on chat. And as I said later, I will also share my slides, and you can post them on the website, no problem. So that's all from my side. So I also would like to thank you. Thank you first of all for the invitation, for inviting me to be here, and thank you for your attention.